Okay, so let's work on a problem on electric force. So generally, electric force problems are ones where you have combinations of different charges and you're expected to figure out the force on one or many of those charges, right? So for example, in this problem, we have three charges, Q1, Q2, and Q3, and we know their locations. They're located respectively at 0, 0, which is the origin over here, x comma 0 for Q2, which is along the x-axis, and then the third one, Q3, is at x1 comma y1, where we will treat this x, x1, and y1 as variables, and so will we treat Q1, Q2, and Q3 as variables. And we are expected to find the net force on Q3 due to Q1 and Q2. Okay, numerical values are given to us. K, we know that the constant of proportionality for electrostatics is that number, 8.99 times 10 to the 9 Newton meter squared over Coulomb squared. And then each of the three charges, Q1, Q2, and Q3, x, and the distances x, y1, and x1 are given to us. But we will not focus on these numbers for now. We are going to solve this problem algebraically. And then later on, we'll come back to these numbers and plug in to see what results we get. Okay, in order to solve this problem, in order to find the net force on Q3 due to Q1 and Q2, clearly we have sort of two forces, right? One on Q3 due to Q1, another one on Q3 due to Q2. And so in order to figure that out, we would first have to figure out the force due to each of these charges on the other charge on Q3, and then add them together. And in adding them together, adding these forces together, we're going to make use of what is called the superposition principle. Right? So principle of superposition or superposition principle, this principle tells us that if we have two forces acting on the same object, then we can add the two forces. That is, F net is just a vector sum. F net vector is just a vector sum of F1 and F2, where F1 and F2 are the two individual forces that are acting on the same object. So F1 and F2 have to be acting on the same object. That's the condition. Okay, so that's the superposition principle. We're going to apply that. We're going to first find the force on 3 due to 1 and then on 3 due to 2. And once we have these two, we're going to vector add them together to get the net force on 3. And of course, these two forces are both have to be acting on the charge 3. Okay, the second ingredient that we need is Coulomb law of electrostatics. So Coulomb law of electrostatics. This tells us that if we have two charges, Q1 and Q2, which are separated by a radius vector, these are point charges separated by a radius vector r, this is Q1, that is Q2, then the force on 2 due to 1 is going to be along that direction, and this force we're going to represent it as F12, force due on 2 due to 1. This vector quantity is going to be equal to K Q1 Q2 divided by r vector squared and then r hat. Or you can also write this as K Q1 Q2 divided by r vector cubed times r vector itself. Okay, both are correct notations. What we have used over here is that unit vector r is just r vector divided by magnitude of r vector, right? So these are the two ideas, superposition and Coulomb law, that we're going to use. So Coulomb law is going to allow us to find individual forces, and superposition is going to allow us to add those forces together to find the net force. So let's start with the first application of Coulomb law. So we're going to start with this situation here. Let's make this diagram a little more geometrically apparent. So what we are doing over here is we know that this distance full from here to here, origin to Q2, that's x. Origin to Q3, that is x1. And then origin to Q3 along the y direction, that is y1. So we know this. Okay, so from that knowledge, in this right triangle that I drew over here, right, that right triangle, this one, the one that is I drew this triangle to show you the triangle that I'm talking, the bigger triangle that I'm talking about here. So if we call this point, so let's call this point A, then the triangle Q1, Q3A, that's the triangle that I'm talking about. And in that triangle, then the hypotenuse over here is going to be equal to square root of x1 squared plus y1 squared, and that's simply using Pythagorean theorem. All right, so with this knowledge then we can apply Coulomb's law and find F13, force on 3 due to 1. That's going to be equal to K Q1 Q3 divided by x1 squared plus y1 squared, which is the square of this quantity, times x1 I hat plus y1 j hat divided by the square root of x1 squared plus y1 squared. And how did I get this vector? Well, I'm really interested in the unit vector that is pointing along this direction over here, right? So if I could draw a unit vector over here, this is the unit vector r hat that I'm interested in for finding the force between Q1 and Q3. And in order to find that, all I have to do is figure out what this r vector is, so the vector from the origin to the Q3. And what is that vector? That looks like x1 I hat plus y1 j hat. And divide that vector by its magnitude, which is square root of x1 squared plus y1 squared. And so that's my answer for F13. All right, we can also simplify this a little further, put these x1 squared plus y1 squares together, so we get k q1 q3 divided by x1 squared plus y1 squared, and this quantity raised to the power 3/2, and the 3/2 is because we are adding the 1 to the 1/2, so 1 plus a half is 3/2, and then this is along x1 I hat plus y1 j hat. And as simple as that. So we have just found F13. Okay, so the next task is to go and find F23. So F23, this force vector is going to now depend on the two charges Q2 and Q3. So we have K, Q2, Q3. And this time the distance is this hypotenuse of this other triangle, right? So triangle AQ3, Q2. So in that triangle, if you again want to apply Pythagorean theorem, then the way to do that is to write, so the y part is unchanged, but the x part, you see that distance is x minus x1. So we have x minus x1 squared plus y1 squared. And this quantity raised to the power 2 because we have 1 over r squared in the denominator. And then in order to find the vector quantity, there we have to be a little bit careful. If you think about it, the vector is going to point, if I can fix this, along. So the vector is going to, the unit vector is going to point along that direction. Okay, so let's change our names. Let's call this R13 hat, and let's call this R23 hat. So we have to find that R23 hat, and that's of course going to be along this direction, along the direction of that dashed arrow over there. And what's the direction of that dashed arrow? That's equal to x1 minus x I hat plus y1 j hat. And let's check if this x1 minus x I hat is correct or not. Well, x1 minus x, as you can see, x1 is smaller than x, so that's a negative quantity. So really this vector is pointing along the negative I direction, negative x direction, and the positive y direction, which is correct, which is what we want. And then we again have a copy of the square root of x minus x1 squared plus y1 squared. By the way, in the denominator, it doesn't matter if you write x minus x1 squared or x1 minus x squared, because when you square it, that minus sign is just going to go away. All right, so let's put these two together over here, just like we did in the first case. So we will get k q2 q3 divided by x minus x1 squared plus y1 squared, this quantity raised to the power 3/2. And then we have to write the vector explicitly, which is going to be x1 minus x I hat plus y1 j hat. Great. So these two are essentially simple applications of Coulomb law electrostatic interactions. And now all you have to do is put these two together using our favorite superposition principle. So F net is going to be equal to just F13 vector plus F23 vector. And so if I wanted to write it out in long form, what I would have to write is for the I hat component, then we will have K Q1 Q3 divided by x1 squared plus y1 squared raised to the 3 halves, and this comes with an x1 plus x minus x1, or actually x1 minus x times k q2 q3 divided by x minus x1 squared plus y1 squared raised to the 3 halves. So this is our x component of f13 plus f23, and the y component, or the j part of it, will look like the same quantity k q1 q3 over x1 squared plus y1 squared raised to the 3 halves. But instead of x1 over here, we will have y1. And you see that the y1 part is the same for both, so the other side will also be y1 times k q2 q3 over x minus x1 squared plus y1 squared, whole thing raised to the power 3 halves. Okay, so this is our algebraic answer. In order to get our numerical answers, now we have to sort of put all of these together in terms of numbers, and we already have all these numbers. So for the actual numerical calculations, we will use a computer program. But even before we do that, we sort of have to set our numerical values up a little bit. So for instance, we know that K is given in Newton meter squared over Coulomb squared, but Q1, Q2, and Q3 are given in terms of microcoulomb. So it's probably a good idea to convert the charges Q1, Q2, and Q3 into coulombs first, and then K is given in Newton meter squared over Coulomb squared, and the X's, Y's, X1 and Y1 are given in terms of meters, so we don't really have to work that hard to do any conversions over here. But for Q1, Q2, and Q3, we definitely have to do a conversion. So let's do that. So what is 1 microcoulomb? 1 microcoulomb is equal to 10 to the negative 6 coulomb. Okay, so that means that Q1 is equal to negative 25 times 10 to the negative 6, 10 to the negative 6 coulombs. Similarly, Q2 is equal to 15 times 10 to the negative 6 coulomb. And finally, Q3 is equal to 20 times 10 to the negative 6 coulomb. Okay, once we have done that, one can plug this into a calculator, but I personally think that it's easier nowadays because we have computers available to us. It's probably a good idea to do this exercise computationally. So what I would do is I would go to a sort of an online software where we can do these calculations, and here I've done that. So I've written out K, which is 8.99 times 10 to the 9 in appropriate units, and the appropriate units in this case is Newton meter squared over Coulomb squared. And then Q1 is negative 25 times 10 to the minus 6 Coulomb, Q2 is 15 times 10 to the minus 6 Coulomb, so on and so forth. Q3 is also written in coulombs, and then X1, Y1, and X are written in terms of meters. Okay, so once we do that, the next task is to write out the formula for F13. So F13, our formula, and this is a vector. I unfortunately don't have a proper way of representing vectors with the arrows on top of them in here. But that's because this is a computer code, so the computer really doesn't understand exactly how vector variables work, but we can still represent it in terms of what we have done so far. So F13, if we go back to our expression, F13 you see was this expression over here, KQ1, Q3, this first part. We can just take this first part and plug it in, and that's essentially what I have done over here. F13 is KQ1, Q3 over x1 squared plus y1 squared multiplied by the vector x1 I hat plus y1 j hat divided by square root of x1 squared plus y1 squared. And if I run the program, it gives me that since I've used everything in just normal Newton, Coulomb, and meter, and this final answer is a force, we can safely assume that this result is going to be in newtons. I encourage you to actually plug in units at every stage and to make sure that what you get over here is newtons. And it's a good exercise to plug in units at every stage. So we will find that F13 is in newtons, and the final result is going to be F13 vector is equal to negative, let's see, what was it? Negative 0.43. And I'm gonna not bother about significant figures. I'm just gonna keep the first two digits rounded up. So negative 0.43, negative 0.58. So we have F13 is negative 0.43 I hat, negative 0.58 j hat, and then we should write the units. This is in newtons. Okay, let's try to think about it and see if this matches what we expect. See, Q1 and Q2, if you notice, Q1 and Q2 are opposite charges. They have opposite signs. Q1 is negative, Q2 is positive, which means that I'm expecting that this force is going to be pointing along this direction, which is negative x and negative y direction. That's what I'm finding over here. So my answer is probably correct. Well, at least to the extent that the signs are correct, right? Now let's look at F23 vector. So F23 vector, again, we're going to use the second formula over here, right? Either that one or that one, whichever one you like. You can plug it into a computational sort of a software like I've done over here. And then you find that the result is negative 0.15 plus 0.62. Okay, so let's write that. So negative 0.15 I hat plus 0.62 j hat. And again, the units is newtons. Don't forget the units. Okay, great. So at this stage, if I now look at F23, Q2 and Q3, if you remember, Q2 and Q3, they are like charges. They're the same sign charges. So the force should be repulsive, which means that the force should be along this direction over here, along this R23 hat. So that tells me that it should be along the negative x and positive y direction, and that's what we are finding over here. All right, so now what about the net force? In order to get the net force, we just vector add these two together. Vector addition is very simple. You just add the components, component by component, and you see that the y components are almost canceling, but the x components are adding up. So F net vector, that's going to be roughly negative 0.58 I hat and positive 0.04 j hat, and the units are newtons. Okay, just like the computer gave us negative 0.58. This is probably negative 0.59, but that's, the errors are the third digit becomes significant once we have added them together. We don't really need to bother about significant figures at this level, but this is essentially the idea of solving a problem like this. Okay, so I want to make one more additional point. So it's kind of interesting to see how we found the net force on Q3 due to Q1 and Q2. And the only effect of the charge Q3 itself was this multiplicative factor in both F13 and F23, right? There was this Q3 sitting over here. Okay, if I change this charge Q3 to some other value, let's say I change Q3 from 20 microcoulomb to 20 coulomb, all that will change is this numerical value over here in Q3. So one can set up an idea where even in the absence of Q3, there is as if there is some object, some abstract object over here, which when you put Q3 in there, feels the force. And this abstract object is what we refer to as an electric field. Okay, so this is our segue to definitions of electric field. Okay, so electric field, what is electric field? Electric field, for our purposes, electric field would be the electric force on a unit of test positive charge. So in other words, if I wanted to find the E net, okay, E net, electric field will be represented by and capital E with a vector sign. It's a vector. Electric field is a vector. Okay, so this electric field is nothing but E net is equal to F net divided by the charge that is feeling this F net. Okay, so in this particular case, F net is being felt by Q3, so the electric field at 3 due to 1 and 2 is just this F net divided by Q3. Okay, so E net, okay, E net vector, and this at Q3 due to Q1 and Q2, that's just equal to F13 plus F23 that we found before divided by Q3. And that's it, right? So whenever you want to find the electric field, you can just take the force and divide it by charge. All right, so then we can sort of go back to our Coulomb law kind of thing, right? So in our Coulomb law idea, there was charge Q1 over here and then charge Q2 over here, and these two are separated by this radius vector r. So we know that the force due to 1 on 2, this quantity is equal to kq1 q2 over r vector squared times r hat. All right, so now I want to generalize this the idea of field. So what I want to say is now I just have the charge q, and I'm trying to measure the electric field at a distance r vector. So it's kind of similar to this, except now I have to put a unit test charge, find the force, and divide it by the test charge. Well, the test charge is 1, so anything divided by 1 is itself. So we can say that the electric field due to Q, okay, E due to Q at radius vector r, that is equal to KQ. There's no second charge, there's just the charge Q, KQ divided by r vector squared times r hat. Now this is the same result that you would get if you replace Q1 by Q and replace Q2 by 1. So let's look at over here. F12 is KQ1 Q2 over mod r squared times r, mod meaning absolute value of the vector r. So if I replace Q1 by Q, I get KQ, and if I replace Q2 by 1, that just goes away. So electric field then, this is the representation for electric field. Again, this field is going to be repulsive field, as in field lines that would go away from the charge. If electric field lines will go away from the charge if the charge is a positive charge. Why is that? Because the test charge that we always consider is a positive charge, right? So a positive charge will have electric field lines flowing away from it, and a negative charge on the other hand. So if I put a negative charge or an electron over here, field lines are going to point toward it. Okay. All right, so in a different video, we will come back to this idea of electric fields and talk more about how to calculate electric fields. But in this particular problem, instead of asking you to find the net force on Q3 due to Q1 and Q2, the problem could have just eliminated Q3 altogether and asked you to find the net electric field at the location of Q3 due to Q1 and Q2. And in that case, all you would have done is you would have taken this the F13 plus F23 that we found over here and divided it by the charge Q3. Okay, so that's one way of doing it. Alternatively, what you could do is you could just calculate it from first principles without using Q3 altogether, right? So these are two ways of doing it.